All right, good afternoon or good evening from wherever you happen to be checking in from. My name is Joe Steele. I'm the Director of Communications and Legislative Affairs here with Lyft. Thank you very much for joining us for another edition of our Liftoff webinar series, our first international edition of our Lyft webinar series. We're very fortunate to welcome TWI with us to talk about innovations in friction stir welding. We're also going to hear from one of our newest members, Element 6, to talk about how they are partnering with TWI on this new innovation. So thank you very much for joining us again today, wherever in the country or wherever in the world you happen to be. We look forward to sharing this presentation with you. I do have a few housekeeping items to go through before we get started. If you can, put your phones on mute or computers on mute. Everyone should be muted, but just double check that. We are recording this session, so we want to avoid any background noise, as much background noise as we possibly can. Also, we want to encourage you folks to submit questions to be answered during the Q&A portion of the presentation. We will facilitate the Q&A afterwards. So please submit your Q&A session using the Zoom toolbar that you see at the top of the screen. We're all familiar with Zoom and other virtual platforms as we continue to operate in a virtual space. Hopefully you are all safe and well as we continue to work our way out of this pandemic. But in the meantime, please submit your questions and answers there. So for those who are unfamiliar with Lyft, I do want to share a little bit of information about who we are and what we do. Lyft is one of the national manufacturing innovation institutes in the US. There are 16 of these innovation institutes around the country. We are based in Detroit, Michigan, and we are a public-private partnership between industry, academia, and government. Our goal is to take innovations from concept and design all the way through commercialization, as well as ensuring that we have the talent on hand to work with these new innovations when they hit the shop floor. So our goal really is driving American manufacturing into the future through technology and talent development. I know we are talking with some folks across the pond today, but this is our goal. And we know that there are folks around the world that we get to work with to achieve the goals that we both want to achieve. So it's a win-win. And we're doing that through what we call smarter manufacturing. We know that our national economy, our national security rests on the manufacturing sector. We want to make sure that we're doing it in a smart fashion because we know that the next sector, the next region that tackles it is going to come out ahead. And our goal is to work towards that. So what do we mean when we talk about smarter manufacturing? Well, we talk about that by solving the manufacturing equation, and that is connecting materials, the processes, the systems, and talent. So we're looking at manufacturing holistically, not just materials, not just processes, but we want to know the systems that they're going to, that those components are going to end up in. And as I mentioned before, we want to make sure we have the talent on hand to work with those innovations when they do make it to the manufacturing floor. So materials and processes, I know we're going to hear about that today from TWI and Element 6. So how do we do this? We do this with two programs at Lyft, our technology program, Leading Innovations for Tomorrow, and our talent program, Learning Innovations for Tomorrow. We know that the talent gap that we see around in the US is not a US problem. We know the talent gap exists in advanced manufacturing around the world as well. So I'll touch a little bit on our technology program, Leading Innovations for Tomorrow. You see on your screen here the four pillars of technology that we focus on, all the way from integrated computational materials engineering to agile and smarter manufacturing, like we spoke about, advanced alloy and process development, and multi-material joining. I won't quiz you on what you see on your screen, but a little bit deeper dive into those pillar areas, and you see why it's important to have an organization such as TWI to be a part of Lyft as we're talking about new innovations in welding. That is certainly high on our priority list as we innovate across these pillar areas. On the talent side of the equation, again, it's all about innovation there as well. Starts with our Ignite Mastering Manufacturing curriculum, a curriculum that we developed with funding from the Department of Defense, mostly for high school students, which is taught at our learning lab. Pre-pandemic, we would have 120 or so students participating in this at our facility in our learning lab. participating in this curriculum, learning about material science, learning about introductions to advanced manufacturing. We also offer world-class certification programs for jobs that are available today, both through Lyft and through our program called Operation Next. Operation Next is a program that was launched as a program to help our separating men and women from the military as they leave the military service, provide them opportunity to earn credentials in advanced manufacturing jobs. So that was launched as a pilot at Fort Campbell, Kentucky. It's been expanded to the National Guard in Michigan, as well as in Florida. We're also expanding it to small and medium-sized manufacturers here in the country to try to help them get off the mat from the pandemic, to encourage folks to receive training, upskill training they may have already had, or begin a career in advanced manufacturing. So I mentioned we are a public-private partnership. We are a nonprofit organization. We're also a membership-based organization. So we're proud to have TWI and Element 6 both as Lyft members. So what do you gain from being a member of Lyft? Well, everything you see on the screen here, from being a trusted advisor. We're not here to sell you a specific good or product. We want to give you the best advice we can as it relates to becoming a smarter manufacturer. Technology accelerator, again, bringing technology from concept to the marketplace as quickly as possible. A technology showcase. When you are in Detroit, next time you are in Detroit, Michigan, please come visit our facility when it's safe to do so. We want to show you the art of the possible, but we also, that's where we do our work. We have technicians in our high bay conducting research and development work each day, every day. We are a connector and convener, and today we are taking that around the world. So thank you very much again for joining us today. We're a talent developer and a government partner. We work very closely, obviously, with the Department of Defense, the Office of the Secretary of Defense, but we also work directly with some of the military branches as well. So you may wonder, all this discussion about the Department of Defense and the American manufacturing, why are we talking to TWI and why are we talking about across the pond about manufacturing? Well, as I mentioned, we know that there are smart folks around the world that we can partner with to collaborate on research and development projects. There are unique facilities and equipment on both sides of the pond that we can share and partner with for the benefit of the entire manufacturing ecosystem. We know that there is a shared knowledge base, both on industry and technical data, but also specifically talking about welding, bonding, and joining, things we're going to talk about today. And we know that there are opportunities to share best practices and really reach out to each other's ecosystem and through webinars and workshops. And we've conducted one previous webinar with TWI last fall, and we're looking forward to hearing them today. So while we are focused on the U.S., we certainly are understand that it is a global ecosystem, and we're proud to have had TWI and Element 6 as members today. So that is it for my Lyft in a nutshell. I encourage you to follow us, reach out to us with any questions, concerns. Visit our website, virtual tour if you're not near Detroit, to take a walk through our high bay, and give us a call. We're happy to explain a little bit further about who we are and what we do. But with that, I'm going to turn the presentation over to Nick with TWI to start the presentation on friction stir welding. So Nick, the show is yours.
Thank you, Joe. Hopefully you can all see that screen okay. Good. Thanks for the thumbs up, Joe. That's appreciated. Yeah, first of all, I would like to extend thanks on behalf of all of the team here in the UK to Joe, Addy, and all the rest of the team at Lyft. Obviously, we've had several meetings planning this webinar. They're a great team, great organization, and we really appreciate the opportunity to share this webinar and work with them again. We're here today to talk to you about friction stir welding of steel, the work that we've done at TWI in partnership with Element 6, and we'll all be giving a brief overview of the contribution that we've done to this work. I'm going to just move on to the next slide here. So my name is Nick McCarthy. I'm actually a business development manager at TWI in Cambridge. And I work for a group called the Advanced Manufacturing Technologies Group in TWI. TWI is essentially split up into sort of 4 different groups. Advanced manufacturing technology mainly comprises of the joining technologies within TWI. And so I support 9 sections in TWI with business development. Obviously today the technology that we're going to be talking about is friction technology, but obviously TWI is known for its joining capabilities, and we cover a wide variety of, virtually all of the joining technologies for metals. I'm also accompanied by my colleague Stephen Cater, who will talk about the work that we've done on the development with Element 6, and obviously the 2 gentlemen from Element 6, Richard Townsend and Dr. Santanu Ghosh. So like Joe talked a little bit about how Lyft work and what Lyft work, I thought it would be interesting for those that aren't so familiar with TWI, just to give you a little bit of a background about TWI. We're categorized as an RTO, so a research and technology organization. And a little bit like Lyft, we're not for profit reporting. Obviously, any money that we make is plowed back into research and development and is supporting our membership. So again, another parallel to Lyft, we are a membership organization. We boast truly a worldwide membership, all sorts of different companies, from the very, very big to the smaller companies. And we're all about supporting those members make better products, make sure that they're using the best possible technology to make those products. And obviously, we're very, very much about innovating what we do. We have approximately 600 staff worldwide. Obviously, that moves up and down a little bit. A lot of those are based in the UK, and they are based at 5 main UK R&D centres. I work out of the Cambridge office, which is actually the sort of headquarters for TWI. Like a lot of people at the moment, I'm working from home. Excuse me. But I did manage to get into the office yesterday for the first time this year. So that's good. That's hopefully things moving in the right direction. We also have 12 sort of international offices, which are again there to support members. They support with training requirements, certification, and other challenges that members may have. And besides our sort of industrial membership, we also have professional members. And again, we have sort of 2,000 plus professional members. And all of that has been built over 75 years. So we think we're justified in saying we are a well-established organization. So very, very quickly, those are the sort of 5 centres that we have dotted around the UK. They tend to, Cambridge obviously is a very, very big site, and a lot of the technologies are at Cambridge. But for instance, we have a training, inspection and welding office in Aberdeen, which is sort of geographically placed there to support, for instance, the oil and gas business. Steve, who will be talking about the work that he's done on friction stir welding, is based in our Sheffield Rotherham office there that you can see. And we also have an office in South Wales and in Middlesbrough. Very, very quickly, the sort of 4 main groups at TWI, to use Joe's phrase from his presentation, the pillars, if you like, are advanced manufacturing, materials and structural integrity, non-destructive testing, and non-metallics. And as I said, the advanced manufacturing side is the group that I actually work for. So that gives you a bit of an overview about the broad church that is TWI and the areas that we support. We are, as I said, a membership organisation. That just gives you a little bit of information about the benefits of being a member of TWI, what we have to offer. Obviously, we're supporting with members with challenges that they have with manufacturing, but we offer a lot of other different support options as well. We have, for instance, an extensive library in Cambridge, which I think I'm justifiable in saying is a world-leading library for joining technologies. So being a member, as are Lyft, as are Element 6, obviously you get the access to that and all the benefits that come with that. We work across a broad range of sectors, and that just highlights some of them there. I'm not going to go into them all individually. Historically, oil and gas has been a very, very big area for TWI, but in recent years, with the rise of the electrification agenda, we're doing more and more work, for instance, with automotive manufacturers supporting battery manufacture, which is obviously, plenty of joining challenges there, we're pleased to say, and that's something that we're helping with. So hopefully, again, that gives you an idea about the variety of areas that we work in and how diversified we are. Quick few facts about friction stir welding. I'm very proud to say that friction stir welding was actually invented by TWI in 1991. And, the process, obviously, solid state bonding process, many, many benefits with the process, repeatable, robust, reliable, accurate process. One big one is obviously reduced distortion, etc. Really, friction stir welding, I think most people will know, it's not a secret, has been very widely used for aluminium applications. We're looking at, in fact, aerospace application on the left. On the right-hand side, I think we're seeing a marine or a shipbuilding application. And obviously, one of the big challenges or one of the big questions we've had many, many times is, can you friction stir weld steel? It's been the holy grail, I would say, and it's something I know that Steve has been working on for a long, long time. We have been able to friction stir weld steel, but because it is such a challenging environment for the tool, etc., we've had problems with tool life, with consistency, and all the related issues that come with that. And that drove us to talk to the team at Element 6 and to try and come up with tools, material that would give us consistency. And Element 6 will talk a little bit about that shortly, what they've done, and Steve will also tell you about that. I thought it was just interesting here to give you a few facts about the size of the we estimate the friction stir welding market is currently $50 million approximately, and is very aluminium or should I say aluminum dominated, depending on where you are in the world. Obviously, the steel market is dramatically larger than that. And I think that perhaps gives you an indication as to why we are driving this agenda and that we see huge benefits with being able to friction stir weld steel. We think, initially it will be obviously more niche applications that we're looking at, but we're really excited about the development that we've done and the path forward. That really kind of underlines what I've just said, that it's been a challenging journey so far, but we really feel that we are now making great headway. As I said, we are very fortunate to be joined by our friends at E6, who I'm going to hand you over to now. I'm going to hand you over to my good friend, Richard Townsend.
Thanks, Nick, and also thanks to Lyft for hosting the webinar. What I want to cover today is two aspects. Firstly, maybe to introduce Element 6, and also to talk about why we feel we're in a unique position to develop friction stir welding for steel solution. So for those who don't know us, we're a global company. We're actually part of De Beers, who are in turn part of Anglo-American, and we're proud to be part of a large company. In terms of our locations, you can see there we've got quite a wide spread. We have six, in fact, factories over 6 different countries, and we also supported here where I'm based in the UK, by an innovation centre with a team of about 100 scientists. Now, in terms of US, we have a good coverage. We've got plants in Santa Clara, in Portland. We have a sales office in Houston, and also distributors in Canada and also the US. We've been producing industrial diamond for a long time, for over 60 years, and a wide range of industries and applications. This is aerospace, automotive, semiconductors, and oil and gas as well is a major market for us. And in fact, we have at least 20,000 unique products over, in fact, 5,000 customers globally, so quite a large spread. Next slide, Nick. Okay, so the products we produce are basically very hard super materials. And you can see here, hopefully on the slide, what we produce is in the orange boxes. So it's products such as single crystal diamond, CVD diamond, polycrystalline diamond, which is PCD, and also Pcbn. And that's the material that we are developing the friction stir welding tool from. Now, interestingly, with our high pressure, high temperature press systems, we operate at very high pressure. So to give you an example, the pressure is equivalent to the Eiffel Tower actually standing on top of a can of Coke. So we can imagine that's a lot of pressure. So we've also been producing PCBN for many years, over 40 years. And we've invested a lot in terms of R&D and innovation. And we have the largest bulk discs available in the market. And we also have a wide range of PCBN that we've tailored to the application. So for example, we have over 50 different recipes and products. So this, we feel, is one of the reasons why we're sort of uniquely placed to be able to develop the solution for friction stir welding. Now, in terms of capacity, we also have, we'll obviously produce a lot of PCBN every year. And so when we move from the current development stage into sort of mass production, we're quite confident that we can scale up into large volumes. I think one of the key questions you probably have is also, you know, how do we make sure that the tools are consistent, hard wearing, and durable? But one of the key things is using that knowledge of PCBN. And I think working with TWI has also been critical, supported by our team of scientists here. Now what we're able to do is we're able to control end-to-end process. So for example, we control the powder preparation, the press, the processing of the material, and also the tool prep. And having the testing feedback from TWI is so important. So, I mean, we're really excited by the results we've got so far. And I'd like to pass you over now to Santanu, who will explain in greater detail.
Thank you, Richard, and thanks, Joe and Nick, for hosting the webinar. So Richard talked about in the previous slide about the cycle of development. It took almost 2 years for us in this development process. Before I jump into the details of what we have done and what we are talking about today, let me talk a little bit about Pcbn, which is a short form of polycrystalline cubic boron nitride material. So cubic boron nitride is one of the hardest material after diamond, and it's not naturally available or naturally occurring. So we have to manufacture them in a synthetic process, which is high pressure and high temperature process. Now, most of the ferrous machining and high temperature metal processing, polycrystalline cubic boron nitride is a very important material, is primarily because of their high temperature properties, which includes their hot hardness, for example, their ability to withstand high temperature before you see any deterioration. Now, why those are important for steel is for friction stir welding. Steve will talk about the mechanism of friction stir welding, but for high temperature metals, you need to go to temperature which is nearly 1000 or above 1000 degrees centigrade, which softens the metal. And for that reason, the tool has to survive. Now, for steel and other high temperature metals, that has been a challenge to find a tool material which we could use. Now, for us, when we started, there was two main challenges which appear. One is whether we can get enough tool life, which will make this process viable. And the second one is whether we can produce consistent tool materials so that when it goes into an industrial process, you can confidently set a tool life and use it. So on the life, we have tested the tool till now maximum of 63 meters. And we stopped the testing. It's not because the tool failed. We felt that that kind of length covers a single stretch of length, and in many applications, some of them which Steve will talk about later, will be covered. So whether that's 1 meter, 2 meter, or 20 meter at a stretch of welding, and we could cover that. It's not one tool which we took to 63 meters. We have done it with multiple tools with 60 meters, and the weld quality we have seen remain pretty stable across it. In terms of consistency, we did manufacture 5 different batches over a period of 1 year. You are familiar with manufacturing processes of specifically the materials, you get variation from in the manufacturing process. And if you do that over a period of 1 year, the chances are you will be able to capture most of the variation. So we produced tools out of that, and we ran a trial with around 40 meters of length. In terms of tool life, there is one other factor which those of you who are familiar with ceramic materials, that they are brittle. And in case of friction stir welding, when the tool plunges into the cold steel or the high temperature metal, that's where the tool and the probe experiences higher amount of stress. So we wanted to do plunge tests to see how many plunges the tool survives. And these plunges were not only done with the new tool, it was done at different life. So we have done with the fresh tool, we have done it after 40 meters, and a large number of plunges we did actually the tool which had done around 60 meters. So these tools could do more as we incorporate feedback. And our main objective is now to find the application in which we can make this tool industrially viable. So if you have any application in mind in which you want to try that, please, by all means, contact us, and we will be happy to take it forward. Next slide, please. So in terms of the tool, so Steve will be talking on the weld assessment side, and let me talk about the tool assessment side. So when we ran this consistency trial, along with the weld quality consistency, we wanted to see how the tool wear is happening. Now the tool had shown minimal wear till 40 meters of welding. However, we wanted to monitor how the wear develops. We used a 3D microscope, Alicona, to generate these wear profiles, which demonstrated how the tool wears. So, for example, on the left image, the pink and the red areas are where you see the tool starts wearing. on the right, we made a cross section of those profiles, and you can see after 40 meters of the wear, how nicely they overlap with each other, which demonstrated the wear on the tool has been consistent, and it was reflected on the weld as well. Next slide, please. So we have done quite a lot with these tools. It's not only testing these tools for life or consistency. We did test them at different regimes. So whether it's force control or whether it is position control, we tested them for different grades of steels. So for example, S355, DH36, or so on and so forth. Steve had tested them on other steel and grades as well, and stainless steel, for example. And Steve will be talking a little bit on that. Now, we know that these tools could do more than what we have tested for. We would like to see their performance, and we are quite confident that they will be performing in your application as well. Each application has their own requirement, and the tool design, etc., will rely upon what kind of application which we are doing. So if you have, again, any application in mind in which you want to try these tools, please let us know, and we'll be happy to collaborate. So I'll pass it on to Nick back now.
Yep. Thank you, Santanu. Thank you, Richard. That's really interesting stuff, exciting stuff, and it's great to see what we're doing. I'll pass over to Steve now, who's going to tell you a little bit about what we've been doing at TWI.
Okay, thank you very much. What we see on the screen at the moment is just an example of a friction stir weld in 1/4 inch or 6 millimeter thick carbon steel plate. That's 6 meters long, and it just shows how little distortion we get along the length of that plate. From end to end, we saw just about 2 millimeters of distortion. So that's pretty good going. On the next slide, we'll see some of the steel grades that have been welded. So when we first started welding, we started with just simple plain carbon steel, such as ASI 1018, 1060, which are just iron and carbon. We then gradually worked our way through the alloy compositions. So we started looking at structural steel, such as S2355, some of these steels that are used in the oil and gas industry, such as the API 865 series, shipbuilding steels, such as DH36, HSLA 65, and all the time we're gradually moving up in alloy and carbon content until such time as we reach things like D2 and O1, which many people would suggest are very difficult or even impossible to weld by conventional means. We don't find that problem with friction stir welding. We're not melting the steel at all. We're not changing the chemical composition. And so the carbon equivalent has far less influence upon the process with friction stir than other kinds of welding process. We then did the same kind of thing with stainless steels. So we started with simple stainless steel, such as 304, followed the same process, gradually moving up through the complexity of the alloys, and finally finishing with things like duplex and super duplex stainless steels, and found that we could weld them quite easily. We were then asked, can you weld some of the grades of steel that are regarded as being unweldable, such as the oxide dispersion strengthened steels? And again, because we're not melting anything, we're able to do that because we do not destroy the oxides that are in there to strengthen those steels. We can also weld dissimilar grades. So one of our party pieces, if Nick moves on, is to actually weld carbon to duplex stainless steel, and that macro section through a weld shows the stainless steel being swept into the carbon steel and producing a very good solid bond. If you were to subject that to tensile testing, the failure would occur in the weaker of the two steels, which is normally the carbon steel. The weld itself doesn't fail. We find the weakest part of the carbon steel. Next slide, please, Nick. So we've undertaken a tool assessment program working with Element 6, and we've assisted them with designing the tool holder and the tool design. And most importantly, we've now been undertaking both assessment of the tool wear and the tool, the weld properties themselves. What we should have next is a explanation of the testing that we've undertaken. So we've looked at it in 3 different types of testing. One is where we've been doing multiple short welds, typically about 2 meters long. And this is perhaps typical of repair welding and pipeline welding, where the welds themselves are short and the tool is only at elevated temperature, typically around about 1,000 degrees for several minutes. And the wear life of the tool is probably dominated by the plunge into the cold, hard steel. And that happens multiple times per tool. The second testing regimen that we've been looking at is doing multiple 5-meter long welds, which are probably typical of many kinds of general engineering and modular construction. This requires fewer plunges of the tool into the cold steel, but it does see much longer times at elevated temperature, typically 20 to 25 minutes, soaking there at over 1,000 degrees. And then the final testing regimen that we've been looking at is making just a few welds per tool, but these being much longer, typically 20 meters long, typical of something like welding the seam of a pipe or making a stiffened panel for a ship. And under those circumstances, the tool itself may be sat baking at temperature for well over an hour. So that gives 3 very different lifetimes that the tool may see, and it was essential that the tool could actually survive all of those if it was to be industrially useful. To look at the tool consistency testing, we chose one of those cycles, and we decided to look at the 6mm tools that have been developed, and we took 6 tools from 3 different production batches. We had tested those welding in S355 steel, which is a standard carbon steel widely used. We machined the mill scale from the surface of the plate to give an identical testing condition for every tool. And then we made the welds in position control, making multiple 5-meter long bead-on plate welds. And we were targeting 8 lengths per tool to give a total weld per tool of 40 meters. For every weld made, we recorded the forces, the torques, and the energy input. We recorded the tool dimensions before and after each weld, photographed the tool, and did a laser scan of it every 20 meters to allow the wear to be assessed. Next slide, please. So if Nick runs this video for us, what we'll see is a typical friction stir weld in steel. Initially, the cold tool embeds into the steel, generates heat, and starts to traverse along the steel plate. As you'll see here, we are making multiple welds in the steel plate, effectively trying to wear out the tool. We're doing multiple welds side by side. We're seeing very little distortion. And as you can see, the friction stir welding process has no ultraviolet, no sparks, no fumes. It gives a very nice, consistent weld surface. We carried out that process on tool after tool after tool, building up a huge amount of knowledge as to how these tools would perform over well over 300 meters of welding. And when we have a look at the tools before and after welding, we've seen that when we were testing them to the 40-meter mark, we saw very, very little wear, and the tools were still giving very consistent performance and were capable of producing very good welds, even beyond 40 meters of welding. The next slide, if Nick builds it up, will show us what the tools look like during the different stages of welding. And so between 0 and 40 meters of welding, the amount of wear that accumulated on those tools was negligible. And so the tools were still capable of giving a good, consistent weld. A quick look at the weld sections. These are sections through the welds taken at the 10, 20, 30, and 40 meter marks. And in every case, we've got a fully consolidated weld with no internal defects. So again, that shows that the tools we're offering a very consistent behavior. Next slide, please. So as Santanu's already pointed out, what we found was that the tools were very consistent, both in terms of their wear properties, in terms of the forces and torques needed to make those welds. They were predictable. We've since taken those tools on further, and we've now reached 60 meters of welding on those tools, and they are still producing good welds. So in terms of potential applications, one of the things that we've been looking at is looking to what we can do in terms of maritime and shipbuilding. One of the things we've looked at is that the tools work perfectly well underwater. We can make a weld underwater with no real problems. The very low amount of distortion that we see from the tools is very useful if you're building ships using modular construction. When you bring those parts together, you've got a pretty good chance that they will all fit, which is quite important when you're doing that kind of structure. We've also been looking at alternate ways of manufacturing stiffened panels by welding together rolled T-sections and spacing them apart by plates, and so reducing the number of welds made in a particular structure. A second area of interest is using the tools to weld through a pre-existing arc weld. So on this particular image, what we're seeing is the parent metal, which is 20 millimeters thick, as initially being welded using an arc process, and that's taken 38 passes. And as you can see, the arc welded region has a large columnar grain and a large heat affected zone, and so has very different properties from the parent material. We then ran a friction stir welding tool through the cap of that weld, and that has returned that large columnar grain structure back to a very, very fine grained wrought structure, very similar to the parent material. And so it's perhaps not surprising that we're seeing the friction stir weld having very good properties, at least as good as the parent material. And so that's been looked at as a technique for repairing welds. As well as being able to weld underwater, we've actually shown that the process works under oil. And we've been working with one partner to develop a system which uses a pipeline inspection gauge, or PIG, which can travel down a live oil pipeline as the oil is flowing, detecting defects in the pipe and actually welding repair patches over those defects in the pipe. That's generated quite a bit more interest in the ability to weld things like fuel tanks without needing to drain and purge them. We've also been able to weld dissimilar materials, so welding things like steel, and to materials such as corrosion resistant alloys and some other exotic alloys used in the nuclear industries. And so again, that's creating a lot of interest in potential applications. Finally, on terms of applications, as well as the general engineering things, because we can weld grades of steel and other alloys that have not previously been welded before, such as the oxide dispersion strengthened alloys, and the process is fully automated, you could actually deploy it in an area where you wouldn't want to send a human welder. So there's been interest shown in welding, for example, nuclear fuel capsules, which already contain radioactive waste, because the process can be done automatically and remotely.
Thank you, Steve. Very good presentation. Very interesting to see the work that's going on already and how we're moving forward. And I really hope that gives the webinar attendees some food for thought on ideas and applications that we can look at. And in relation to looking at that, we thought it might be useful to give you a little bit of an overview, if you like, a roadmap as to how we could potentially work moving forward with what hopefully is many inquiries that that you will bring us from this webinar. So really what we see first of all is the first pillar on the left-hand side is effectively potentially an inquiry that comes in, which could come directly into the Lyft centre. It could come to TWI or E6. And at that stage, how we would envisage sort of looking at that is that's our can it be done stage. So typically TWI would be involved there in looking at the application, working with element 6 to see whether we think that is feasible. The next stage would be what we would call the sort of validation phase, which is effectively looking at potentially then doing some welds, working out WPS, looking at economics, prototypes, and even moving into obviously the next phase of industrialization. What are the equipment costs? And what we see as a potential route forward there is that we would work with a Lyft associate possibly in the US, and that could be somebody like Bond Technologies in Indiana, who we both regularly talk to, and in fact both count as members as well. Obviously we're very familiar with their equipment. It could be another equipment supplier as well, to be fair. And then obviously that moves into the sort of implementation phase, where you would be talking directly to the equipment supplier, and element 6 would be supporting with supplying tools, and obviously Lyft and TWI are still in the background there to offer support. So really, I'm trying to sort of demonstrate that this is not just all about research. This is about looking at applications from start to finish, to actually being able to support and provide equipment to bring that process in-house or your preferred method of producing the parts. So that concludes the presentations from TWI and Element 6. I'm actually going to stop the share now, and I think Joe will be analysing the questions that we've had. Joe, hopefully there's a lot of questions, and we'll be asking us some questions, and hopefully we can answer those. I think if we can't answer them all in the limited time we've got left, we will of course follow up and answer them after the webinar. Thanks, Joe.
Absolutely. So if you do have a question, please submit it via the Q&A function, and we can try to get as many of these asked as we can. But if we do not get them all, I know I will send the questions over to the team, and the team will respond appropriately. We're also recording this session. I mentioned someone asked if the presentation will be shared afterwards. It will be shared on our website at lyft.technology, and I think TWI will have a copy of it available as well. So you'll be able to revisit the presentation or share it with folks who were unable to make it today. So a couple of questions. I'm not sure who to direct them to, so we will just I will just direct it to the team, and you guys can jump in. Can you talk about the quality of friction stir welding with non-ferrous metals like titanium or aluminum alloys, nickel-based aluminum, in terms of grain structure?
Yeah, I think I can answer that one. The process was actually invented specifically for aluminium alloys 30 years ago. So we've got a lot of knowledge of what happens with those. And over time, it's been spun out into magnesium, into copper and other alloys, and steel is the latest one. If you think about the process itself, it's a solid state process and it's a forging process, whereas conventional welding is a casting process that melts the metal. Because we're not melting the metal, we don't get any of the grain growth or the phase changes that you see in conventional welding. What we do get is a fine-grained wrought structure. So the properties of a friction stir weld are very much forged properties rather than cast properties. So typically in aluminium, you'll see a recrystallization of the weld zone, very fine grain, and that gives it very good strength, usually very good fatigue properties as well. And so that's why it's widely used in applications that want very high performance at minimum weight. Because in general, the friction stir weld outperforms a conventional weld.
All right, this one came in for Santanu. What is the most challenging failure mechanism? Is it brittle fracture? Is it abrasive wear, or is it fatigue? What do you find most challenging there?
Well, on the tool, the runs we had till date, we didn't have any failure or through fracture during in operation. What we do see is wear, and as I showed in that image, you see wear, larger wear on the shoulder area, and so on and so forth. So that's predominantly the major wear we have seen. None of the tools in this trial I would consider them have failed. We can use all of them beyond that.
You mentioned the wear on the tool. How is that measured? Yeah,
so we use a technique called referencing and measuring the differences. So what we do that we scan the tools in 3 dimensions before the testing, and then we run the trial. We reference it in such a way that the tool goes back into the same positions, and then we run the scan again. And in the software, we measure the difference between the two tools. Not the same tool, but in 2 different wear length, and then we subtract and get the areas and local zones where we see wear. That's one way, and the other way is that we do cross-section measurement. So we look at the profile after certain distances and then overlap them to see which are the areas where we are seeing wear. Both has different insights that we get, but that's typically what we use the 3D microscope to do that.
Got it. So in one of the examples you showed was a plate where it had been welded together, and the question is whether or not some kind of fixturing or clamping was used to control the distortion, because it was noted that there was negligible distortion at the time. So was there any clamping or fixturing used, or was it a matter of the process that was able to control it?
It's a mixture of both. We use clamping simply to stop the tool pushing the plates apart. Because we've not got any melting going on, if we force a solid tool between those 2 plates, it will just push them apart. So you do need constraint on those plates simply to stop them A, pushing apart, or B, attempting to spin when the rotating tool hits them. That has the secondary benefit that it does hold the place in part, but we're not relying on that to minimize distortion. The real benefit from distortion comes from the fact that in conventional fusion welding, you go through a phase change from solid to liquid and back to solid, with all the volumetric changes aligned with that, and a large thermal input as well to melt the material. In friction stir, we remain in the solid state, so we get no volumetric changes. We're only putting heat just around the tool, so we're not putting a huge amount of heat. Itself can cause distortion. So the greatest benefit comes from the lack of heat input, but the fact that you're clamping the plates down does give a secondary benefit as well.
Got it. So talking a little bit about friction stir welding again, does it possess any metallurgical advantages over arc welding specifically?
Very much so. Again, we're not melting anything. So if we're not melting anything, you can't boil any of the elements off, you can't get segregation, you don't get migration of elements across the joint line and so on. As you could see on that macro of the carbon to stainless steel, there's no alloying going on there. It's a pure joint line mix. We are controlling the grain structure. We're not removing any strengthening carbides. So metallurgically, it is a very much better process than conventional welding techniques.
Guys, I kind of open this, we're a few minutes left, so I'll open this last question to everybody. And what is your opinion on the next big challenges to be addressed by friction stir welding of steels? Is it reducing the tool cost? Is it increasing possible depth? What are the next big challenges to be addressed with this method?
I think I'll start the ball rolling on that one, Joe. Obviously, we're hoping the next big challenges for friction stir welding of steel partly come as a result of this webinar. so we're looking forward to addressing, you know, the challenges that the attendees bring us on this. Definitely, I think. You know, obviously, as Steve has demonstrated, we've worked with, you know, we've done quite a bit of work with the development already, but we've worked with certain thicknesses. But we're really looking forward to those other opportunities coming forward and other challenges coming forward. As far as the cost of the tools, you know, that is quite a common question that we get asked. I'll pass that one over to Richard just to mention, because I know Richard is well practiced in answering that question.
Thanks, Nick. Yeah,
okay.
It is obviously a normal question. I think at this point we're still in development and we'll be moving into mass production, hopefully in not too distant future. One of the things is that we expect the tool price to be similar to the other Pcbn solutions that are on the market. I think what we're aiming is at having, I guess, a unique selling point is the fact that what we're seeing at the moment is, you know, the distance that we can weld with particular one tool. On the quality, so we're very happy with that. And so also, I mean, there will be different sizes as well that we want to enter with the market, so there will be different pricing on that as well.
Steve or Santanu, anything to add to looking forward into the future?
Well, yes, one point which Richard touched upon is the thickness of the plates. So we have done with the 6 millimeter, but in any applications, as you know, that we have to have multiple thickness of the plates which goes in. So and different tool sizes for that is something that we are looking at. We are developing as well with for tools for larger thickness plates, etc. But that's on the tool side. I think probably Steve can give some on the metal side.
All right. Well, we are just about out of time. I do want to thank TWI, Nick and his team. I want to thank Element 6, Richard and his team for the presentation day. I want to thank everyone for joining today. Again, sorry we didn't have time to get to everyone's questions. But I will forward them to the team here and they will be able to follow up with you directly afterwards. In the meantime, this session will be recorded and posted on our website at lift.technology. I would like you guys to reach out to us, reach out to TWI, reach out to Element 6 so we can all work together to advance manufacturing and these welding techniques going forward. So thank you very much for your time today. We certainly appreciate the presentation. We appreciate your membership. Both TWI and Element 6, so thank you very much for that, and I hope everyone has a great rest of the day.
Yeah.
Thank you so much, everyone.
Thank you. Thanks, Joe. Cheers all.